To get started with interference, imagine that we have two plane waves that are coming in at slight angles to one another hitting a viewing screen. Now, if we want to go ahead and calculate the interference pattern on that screen, first thing we'll need to do is pick a particular point on the screen to calculate our resultant intensity. So let's just go ahead and pick, for example, this point, which I'm going to call point P. And then what we need to do is figure out how far each of the waves has traveled from some reference point. So we're going to assume that both waves start in phase at some point. And so for each of these waves, we have a path length that we need to consider. For this guy right here, this ray has length S2. For this field right here, we've got a path length of distance S1. And so that's essentially how far they've gone from their source, which we're assuming are in phase with one another. So the resultant field at point P then is simply the sum of the two electric fields. Now what we actually observe, of course, is the irradiance, which we can get from the Poynting vector, which is just this term right here. But if you remember, we can rewrite the magnetic field using this relationship right here to get an equation for the irradiance strictly in terms of the electric field. So at point P, what we're going to get is take the sum of those two electric fields, just E1 and E2. I've dropped the notation indicating that these are at point P, but just remember that these electric fields here are being calculated at point P. And so when we take the dot product of these two terms, this is what we get for our result. Now notice that we have that term there, which is simply going to be related to wave number 1, this term right here, which is related to wave number 2, and then this term right here, which is an interaction between those two waves. That's going to end up being our interference term. Now, just to remind you, the bracket term that we have here, this is indicating a time average. And so we're time averaging over a single period. Now, in practice, when we're using a device to measure these fields, it's actually averaging over time that's much, much longer than a period. But from a mathematical perspective, from a theoretical perspective, we can just go ahead and average over a single time period. Now, it turns out that the time average of a sum, in other words, the time average of A plus B, is simply the time average of A plus the time average of B. And we're going to go ahead and use that to break this guy up into smaller terms. And then the other thing we're going to do is rewrite this term and this term here in terms of the irradiance that you'd see just from the each individual light field by itself. So for this term right here, we can rewrite this as the irradiance of light ray 1, and this right here is the irradiance of field number 2. And just to show you how we get to that, so go ahead and assume that we start off with a electric field that looks like this. And so when we take the dot product of that thing with itself, what we end up with is just E1 dotted with itself, which is going to be the magnitude E, not 1 squared. And then we end up with a cosine squared term. Now, if you take the time average of the cosine squared, we end up just getting a factor of a half. And to see that, the time average is essentially integrating whatever's inside here over a single function and then dividing by our total time. This is going to end up being equal to just the period t. And so what we end up with for our time average of E1 dot E1 is just 1/2 of the magnitude of the electric field squared. So what that means then is that the irradiance of light ray 1 is given by this right here, and similarly for light field number 2. So when we go back, this then is what we get for the total irradiance at point P. In other words, the light intensity that we'd see just from field number 1 plus the light intensity that we'd see from field number 2, and then this term right here, which is actually the interference term, and we're going to take a look at that in more detail.